Hello friends, welcome to HP Mathematics Academy. In this particular lecture, we will discuss about the strings in two dimensions. So let's begin. So this is also known as common catenary. Okay, so let us understand this term, the catenary first. Okay, so for this, let us take 2 points. Okay, let us take 2 points. And the condition here is that these 2 points are not in a vertical line. Okay, so these 2 points are not like this. Okay, so this is not in a vertical line. Okay, so these 2 points, let us consider these 2 points, and there is a flexible string that is being hanged between these 2 points. Okay, so a flexible string is being hanged between these 2 points. Let us take this point as A and B. Okay, so it is generating a curve. So this curve is called catenary. Okay, and let us consider the length of the string as L. This whole length is L. Okay, so the weight of this string is concentrated throughout its length, throughout the length of this string. Okay, so if the weight per unit length of this string is constant, then we can say that this catenary is catenary that is curve generated by this flexible string is common catenary. Okay, let us go back to the statement. What is a catenary? When a uniform string or a chain hangs freely under gravity between 2 points, these are the points that are not in a same vertical line. Okay, so these 2 points are not in a same vertical line. The curve in which it hangs is called a catenary. So this curve is called a catenary. Okay, and what is a uniform or common catenary? If the weight per unit length of the suspended flexible string, flexible string is constant, then the catenary is called a uniform catenary. Okay, so we have the 2 equations under this topic of common catenary. First one is intrinsic equation and second one is the Cartesian equation. So the intrinsic equation is S is equal to C tan psi, and the Cartesian equation is y is equal to C cos hyperbolic x upon C. So let us prove this. Let us prove first the intrinsic equation of a common catenary. Okay. So under this topic, we have to understand, we have to study the catenary under which these 2 points are in a same horizontal line. Okay, so we have to study these cases where these 2 points are in a same horizontal line. Okay, so we have to not study this case where these 2 points are not in a horizontal line. Okay, so these 2 points are not in a horizontal line, but in this case these 2 points are in a horizontal line. So we have to study this particular case. Okay, let us understand this in detail. Let us draw a common catenary. Okay, so these 2 points are in a same horizontal line. Okay, and this is the axis of the catenary, and this is directrix. This is the directrix of the catenary. Okay, this is the vertex of the catenary. So these are 2 points. Okay, now let us consider a point P here, and the vertex of the catenary is, let us consider this as point A. Okay, and as we have studied, in case of a common catenary, weight per unit length, weight of this string, weight per unit length is equal to constant. So let us take this as small w. Okay, so small w is the weight per unit length of this string. Okay, now let us consider this length of this string AP is small s. Okay, and this distance of this point A from the directrix is small c. Okay, and let the tension at point P is T, and tension at point A is in the horizontal direction. Obviously, let us take this as T naught. Okay, so now at all the points, the tension in the horizontal direction will be equal to T naught. At all the points, the tension in the horizontal direction is equal to T naught. This is also T naught. In the horizontal direction, the tension is constant. Okay, now let us extend this, the direction of the tension. Let us extend this direction of the tension. The angle that direction of the tension is making with the directrix is psi. Okay, so this angle will be psi. Okay, so in the horizontal direction, the component of this tension is T cos psi, and in the vertical direction, the resolved component of this tension is T sin psi. Okay, so now let us analyze this string AP. Okay, so this string AP is like this. Okay, this is of length S, this is A and this is P. So at point P we have the tension in this particular direction. At point P we have the tension is in this particular direction. This is tension T. Okay, and with the horizontal, this tension T makes an angle psi. So in the horizontal direction, this is T cos psi, and in the at this particular and at point A the tension is in the horizontal direction. Okay, and point A we have the tension as T naught. Tension as T naught. Okay, now we have the string from A to P. Okay, so length of this string is S, and we have the weight per unit length is W. So the total weight of this string will be weight capital W. Weight of this string will be small w into S, weight per unit length into S, and this will act at a bottom, at the center of this. Sorry, this will act at center of this string. Okay, so this is the midpoint of this length string. So the weight ws, a small ws, will act at this particular point. So let us resolve horizontal and vertical component. So we have, this is the horizontal component T cos psi, and the vertical component will be T sin psi. Okay, so resolving horizontal and vertical component, we have T naught is equal to T cos psi, and Ws is equal to T sin psi. So from here we have, let us divide this. So equation, let us take this as 2 and this as 1. So 2 divided by 1. So we have this as tan psi sin psi upon cos psi, and ws upon T naught. Okay, so we have this as tan psi is equal to ws upon T naught. So we have tan psi is equal to ws upon T naught. Okay, so we have tan psi is equal to ws upon T naught. Okay, so now we have to prove that the intrinsic equation of the common catenary is S is equal to C tan psi. Okay, so this we have to prove. So we have the value of tan psi is ws upon T naught. Okay, so what is the value of this T naught? Okay, so for this let us go through this statement. Okay, let us go through the remark 3. The tension at the lowest point is equal to weight of the string of length C. So the tension at the lowest point is A. So this value of T naught, is equal to weight of the string of length C. Okay, so suppose the length of the string is C. Okay, suppose the length of the string is C. So what will be the weight? Weight will be weight will be weight per unit length into length. So this is small w into c. Okay, so the tension at a point, tension at the lowest point, the tension at the lowest point is in the horizontal direction, that is T naught. So based on the remark 3, we can say that T naught is equal to WC. Okay, so let us place here. So this is equal to Ws upon T naught is equal to Wc. So this gets cancelled. So this is equal to S upon C. So we have tan psi is equal to S upon C. So S is equal to C tan psi. Okay, so this is the intrinsic equation, intrinsic equation of common catenary. Okay, S is equal to C tan psi is the intrinsic equation of the common catenary. Okay, so now let us discuss this remark 1 and 2 also. The horizontal component of the tension at every point of the catenary is same and is equal to T naught. So this we have already discussed. So the horizontal component at every point, is equal to horizontal component of the tension at every point of a catenary is same and is equal to T naught. This we have already discussed, and that is equal to tension at the lowest point. So this is the tension at the lowest point, that is T naught. In the remark 2, vertical component of the tension at any point of the string is equal to weight of the string between vertex at that point. Okay, so the tension at any point P, let us take this as point P. The tension at any point P, vertical component. So the vertical component of is this one. So this is let us take this as Ty, and Ty is equal to vertical component of the tension T. Let us draw this again. Okay, so we have a common catenary like this. These are the horizontal points. This is the axis. This is the directrix. So any point P. Okay, so tension is in this particular direction. Okay, so this is the horizontal component. This is the vertical component. This is the angle psi. So let us take this as Tx. This as Ty. Okay. So the vertical component of tension at any point of a string is equal to weight of the string between the vertex and that point. This is the vertex. Let us take this as point A, and this is the point P. So the vertical component of the tension is equal to weight of the string between point A and the point P. Let us take this length as S. Okay, so what will be the weight of this length, weight of the string of length S? This is obviously weight per unit length into length. This is Ws. So Ty is equal to Ws. Okay, this is the as per remark 2. Okay, so now let us go back to the this intrinsic equation of common catenary and Cartesian equation of common catenary. Okay, so we have the intrinsic equation of the common catenary. S is equal to C tan psi. This we have already discussed. Now we have this Cartesian equation of common catenary. Y is equal to C cos h x upon C. This we have to prove. So let us prove this. How we can prove this? Okay, so how we can prove this? So we have the intrinsic equation of common catenary. Common catenary is given by S is equal to C tan psi. Okay, so we have the catenary like this, common catenary. So at part, let us take this as lowest point. This point A is the lowest point, and this is the axis of the catenary. This is directrix. Okay, so let us consider a point P here. Tension at this point P is in this particular direction. This is tension T. Okay, so this line, let us extend this. Okay, so this line of this tension make an angle of psi with the horizontal. Okay, so along the horizontal direction, this angle is psi. Let us resolve this tension T. So this is T cos psi, and in vertical direction this is t sine psi. Okay, and this t on and at point, that lowest point, we have the tension is in this particular direction, that is t naught. Okay, at lowest point the tension is t naught. So we have this this angle psi. Obviously this angle psi will be equal to the slope of this curve. So we have, and let us consider this point P as x and y. So tan psi is equal to dy upon dx. Okay, and let us take this as small p. So this is tan psi is equal to dy upon dx, and let us take this as small p. Okay, so we have this as s is equal to c tan psi, we can write as dy upon dx. Okay, now let us differentiate this with respect to x. So we have ds upon dx is equal to c d2y upon dx square. Okay, we have dy upon dx as p, so we have d2y upon dx square is equal to dp upon dx. This is equal to c dp upon dx. Okay, so we have the length of this string as s. Okay, so now let us take the differential length of this s. So this is s ds. Differential length of this s is ds, and this is dy, and this is dx. So we have ds square is equal to dx square plus dy square. Let us take this under root. So ds is equal to under root dx square plus dy square. Let us divide this by dx. Okay, so this will be equal to upon dx ka whole square. This is equal to 1 plus dy upon dx ka whole square under root. So ds upon dx is equal to dy whole square. Sorry, this is 1 plus dy upon dx we have taken as p. So this is 1 plus p square under root. So ds upon dx is equal to 1 plus p square under root is equal to c times of dp upon dx. So we have dx upon c is equal to dp upon c, sorry, dp upon 1 plus p square, dp upon 1 plus p square under root. So this is, now let us integrate both sides. So we have x upon c plus a is equal to sine hyperbolic inverse p. So x upon c plus a is equal to sine h inverse dy upon dx. Okay, now let us take x is equal to 0. So when at x is equal to 0, we have the slope as dy upon dx as dy upon dx at x is equal to 0. So point A is x is equal to 0, and at point A we have the slope is in horizontal direction. So we have dy upon dx is equal to 0 at point A. Okay, so when x is equal to 0, that is at point A, we have slope, that is dy upon dx is equal to 0. Since dy upon dx is 0, so this whole value will be 0. So 0 plus a is equal to 0. This means a is equal to 0. So from here we have x is equal to c times of x is equal to c sine h inverse dy upon dx. X is equal to c sine h inverse dy upon dx. Okay, let us further simplify this. So we have value of x is equal to c sine h inverse dy upon dx. So from here sine h inverse dy upon dx is equal to x upon c. So we have dy upon dx is equal to sine hyperbolic x upon c. So from here dy is equal to sine hyperbolic x upon c dx. Let us integrate this both side with respect to x. So y plus b is equal to, sorry, y is equal to cos h x upon c divided by 1 upon c. So this will be c. On integrating this will be 1 upon c plus b. B is the constant constant of integration. So y is equal to c cos hyperbolic x upon c plus b. Okay. Now at point when x is equal to 0, the value of y will be this particular distance, and this particular distance is small c. Okay. So this distance, the distance of this point A from C is the distance of this point A from the directrix is c, and when x is equal to 0, the value of y will be this particular distance, that is c. So when y is equal to 0, when y sorry when x is equal to 0, when x is equal to 0, the value of y will be, when x is equal to 0, the value of y will be, okay. So we are taking this particular distance, this particular directrix as a reference point, okay. So when x is equal to 0, the value of y will be this particular distance, that is c. So y is equal to c, so c is equal to c times of cos h. X is equal to 0, this means cos of hyperbolic 0 is 1, c into 1 plus b. So from here b is equal to 0, so this particular value is 0. So we have y is equal to c cos h x upon c. So this is the Cartesian equation, Cartesian equation of common catenary. Okay, so we have two equations. First one is the intrinsic equation, and second one is the Cartesian equation. So let us write down here. So we have intrinsic equation, and second one is the Cartesian equation. So the intrinsic equation is s is equal to c tan psi. Okay, and the Cartesian equation is y is equal to c cos hyperbolic h x upon c. Okay, so this is the Cartesian equation and this is the intrinsic equation. Okay, so we will discuss further concepts in next particular lecture. Thank you.